Okay, thank you for the kind introduction, and I would like to thank the organizers for inviting me here. I've enjoyed the stay in Corsica. Okay, so this is my title. So I realize that I am a mathematician. So most of them are coming from physics. So I will try my best to fill the gap between my to fill the gap among how we deal with the problem about the energy cascade and turbulence flow in the mathematical point of view. So if you have some questions, please feel free to ask me. Okay, this talk is based on the joint work with my colleague Takeshi Matsumoto in Kyoto University in physics, Department of Physics, and Yuta Tsuji, a former PhD student. Okay, so in this talk, I'm not using a Navier-Stokes equation. I propose a one-dimensional hydrodynamic partial differential equations that generating a turbulent flow with the entropy cascade. Okay, so and I would like to understand how mathematically rigorously to understand how the turbulent flow can generate the turbulent cascade. Okay, okay. So here is an introduction from a mathematical point of view. So cascade phenomena in turbulence is famous, according to the famous Kolmogorov theory of turbulence, when the energy dissipation rate, which is given here, is greater than strictly 0 when nu tends to 0. That means that in viscous and non-zero zero viscous limit, then by using the some dimensional analysis, Kolmogorov stated that the statistical law of energy spectra is subject to this scaling law. C is some constant, epsilon is this energy dissipation rate, and K is spectra. So when this prediction agrees very well with many experiments and simulations. This is a picture taken from the book by Kaneda and Goto in 2002. So there are atmospheric data and boundary layer data, boundary layer and smooth data. Anyway, so we can see a good agreement of the energy cascade, like that is following with this k to the minus 5/3. So in this sense, this prediction is very good theoretical result concerning about the decay of this phenomena. So and we also see that there is some region of wave numbers. So you may be very familiar with called inertial ranges, where this prediction is realized. So it is a physical point of view. So mathematical point of view, it is very contradictory situation, because energy, which is a conserved quantity for strictly inviscid Euler flows. But on the other hand, this phenomena indicates that the energy dissipates in the zero viscous limit. That suggesting us that some sort of a singular limit appears in the fluid equations. So the goal of the mathematical studies, one of the mathematical goals to study the turbulence phenomena is to describe this cascade phenomena of the inviscid invariant, such as energy or entropy, etc., in terms of solutions of a hydrodynamic equation. This is my the motivation to study the fluid dynamic equations. Okay, so this is a mathematical point of view. So on the other hand, unfortunately, as you know, it is extremely hard to obtain the global existence of solutions for the three-dimensional Navier-Stokes equation. So this is far away. It is far from complete understanding about this objective. So this is why I'm going to introduce some much simpler one-dimensional hydrodynamic equations to understand, to get more insight about the cascading of the invariant quantity. So this is the motivation of the present talk. Okay, let's move to the next slide. Okay, so I'm going to explain how we derive the one-dimensional equation from the 3D Euler equations. Okay, so I need to be more. Okay, so the equation, the Euler equation is the equation for the velocity field, which is expressed by u of xt. X is a location at some point in R3 space, and t is time. Okay, and also we can define the curl of the velocity field, and which is called the vorticity field. So when we, and the 3D Euler equations can be represented by this vorticity, so which is called the vorticity equations. So this is the expressed formula for the vorticity equation. This is rigorously the same as the Euler equations, in which we can see that the material derivative of the vorticity, which is defined by this, is equivalent to this some quadratic nonlinear term, which is omega nabla u. And so when we, with some initial data and then some initial boundary conditions, we have to think of the solution of this vorticity equation to understand the 3D implicit flow field. So it's, at a glance, this equation is look like an equation for the two functions, but it's not the truth, because the velocity field u and omega are connected through a famous Biot-Savart formula, so which is given by here. U of xt equals to some this kind of the integral. Okay, so when we know the vorticity, the velocity u is recovered from the vorticity field. In this sense, this equation is an equation only for the vorticity. This is a starting point how we derive the one-dimensional model. Okay, so here we make some observation, mathematical observation of this nonlinear term. So the quadratic term omega nabla u is rewritten by an operator form d of omega omega when we plug this equation into this one. So that means this d of nabla u, taking nabla of this singular integral, so then we can say this equation can be rewritten in terms of the quadratic and nonlinear, non-local quadratic term. So this is the rigorous expression for the 3D Euler equation in a closed form of omega. Okay, so this is okay. So the next step we are going to do is to reduce this equation into one-dimensional model based on some observation of this Biot-Savart formula. Okay, so the Biot-Savart formula D is strictly speaking, D is a derivative and the nabla of this Biot-Savart formula. Okay, so when the property of operator D, this is of course this is a singular integral operator, and also it is represented by the convolution of omega with a kernel which is homogeneous of degree -3, which means this is a singular integral. And also, this is a convolution with respect to the kernel here, which is singularity of this kernel is dimensional space 3. Okay, so based on this observation, we can have the 1D and the analog of this operator d of omega, which is a famous and known Hilbert transform. As you can see, this is the h of omega is 1 over pi, the principal value integral from the minus infinity to infinity. This is a convolution of the kernel x minus 1, which is a spatial dimension is 1. So based on this observation, when we write down the 3D vorticity equation into one-dimensional model, we can mimic this d omega omega is something like h of omega omega. So based on this analogous observation, Konstantin and Lux Maida, who are the famous mathematicians, has derived the model equation for the vorticity, which is known as CLM equation. So as you can see here, the time derivative of the vorticity is given by, it grows as this quadratic term. So originally speaking, they are trying to solve this equation explicitly and derive the analytic solution to show the blow-up of the solution. Because of the existence of solution for the Euler equation is also now a problematic problem. So it's a difficult problem to solve. Anyway, so this is a starting point. So here summary, so this is a 1D analog of 3D vorticity equation. But when we compare this equation with this equation, as I said here, this term is represented by h of omega omega, but we miss something, advection term. So in order to make this, make this equation as a more mathematical relevant model for the 3D Euler equations, we need to add an advection term. That is why I introduced the advection term in this Konstantin-Lax-Maida equation. So this equation can be originally derived by De Gregorian, an Italian mathematician, to introduce the advection term, but we generalize this equation by introducing some real parameter A in the equation. Okay, here also you may remember that this Vx omega is given by here, which is h of omega omega. This is the same as the Konstantin-Lax-Maida, and this is an additional term, and A is a parameter introduced to see the balance between these two quadratic and nonlinear terms for the existence of solutions, or some properties of solution. So this is the starting point. Okay, so this is not the turbulent model, but this is the very fundamental type an equation that's based to make turbulent equations later. Okay, so before moving to introducing the turbulent model we are proposing, we have to remind you some sort of mathematical results on the existence and of solutions. Because I'm a mathematician, so we are very concerned about the existence and solutions. Okay, so in order to deal with this, we usually introduce some function space. The notation here is here. L2, so we also consider the periodic boundary condition to make the situation much easier. Okay, so when we consider, when we write L2, S1 is a periodic boundary condition. This is L2 function. And the average of function of this and one period is 0. On the other hand, so when we write hk to the s to the kth, Hilbert space, which is given by here, f has an Fourier transform, and whose coefficient satisfies this decay rate condition. K is here. This is somewhat similar to the function of the case differentiable function in the L2 space. Okay, this is and this is also familiar with most of the people who are listening to this talk. Okay, so anyway, so to avoid the confusion of the notation, we use the L2 and the LHK as a function space to express my mathematical result. Okay, so I'm going to just show, this is a result of mathematics. Okay, so we have some introduced result. So for the first step we need to do is the existence of a unique solution. And local means a locally in time solution. So here the statement is here. If the parameter A is any number, or real numbers, so for any vorticity, omega 0 is given, then there exists some finite time capital T, which is depend on this parameter and the initial data, such that the solution exists in this very long functional space. You can see this one. So C0 is a continuous function with respect to time, and C1 is the first derivative allowed for the L2 space. Anyway, so this is some sort of the very smooth solution can be exist for this unique of this equation for some time t. So next step we need to consider is the existence of solution for all time. But this is another issue because we have to show the solution never blows up in finite time. So, but this is a very difficult problem, as a matter of fact. On the other hand, we have some sort of sufficient condition for the global existence of solutions, which is also stated like this. So this is initial data, which is the H1 space, and the solution exists at some time t. Okay, t is given by here. If the solution of this solution satisfies this integration, which contains L infinity at the maximum norm of this Hilbert transform of omega is finite, then we can extend the solution at some time So by repeating this step, even if we show the solution, local solution satisfies this estimate, then the solution can be extended at any time. That results in the global existence. But unfortunately, it is extremely hard to show this mathematical formula, because this is, some people know this is a famous Beal-Kato-Maeda criterion for the 3D Euler equations. This is a similar type of criterion. So that means, so mathematically speaking, this is very difficult to prove the criterion for the local solution. But we can try to check this condition are satisfied by many solutions numerically. So here is some numerical result. So for given A, alpha is A, we can compute an approximate solution by using the Fourier expansion, a kind of the FFT, Fourier expansion method. So then we can check this quantity for this numerical solution. As you can see here, when alpha is 1, this is a linear function. And when alpha is greater than some value, here, so then this is still finite, but this is grow up very large numbers. So that means, numerically speaking, there is some parameter AC, which is near the 0.6. The solution exists globally. In this case, the solution blows up in finite time, but in this case, the solution exists globally in time. This is a numerical conjecture, so which is stated as follows: if there is some constant AC is near the 0.6, such that the solution to the equation exists globally in time, but if AC is greater than A, it is if AC is less than this quantity, the solution blows up in finite time. This is a mathematical conjecture, but has not proven yet. Okay, so another gradient we have to take care about this kind of 3D model and model Euler equations, with the existence of invariant quantity. This is also shown like this, which is said here: if A is negative, then the solution LP norm of omega is conserved for all time. Okay, so this is an LP norm of the initial data. This is an LP norm of the solution, which is conserved. And the P is given by minus A. So this proposition suggests us some possibility to construct the energy, some sort of the cascading phenomena for when we take the A equal minus 2. Because the turbulent flow with the cascade, which is entropy, omega L2 norm omega, is conserved. So that's why we pay attention to the special parameter A equal minus 2 in what follows. Okay, up to now, I have introduced some 1D hydrodynamic equation that resembling some sort of the mathematical properties of 3D Euler equations. So based on, we have some invariant quantity, implicit invariant quantity. Okay, so correcting these mathematical code into one, we are now creating the equation, the hydrodynamic model for the turbulence. This is very simple. This is the 1D Euler equation that I have introduced. And the local solution exists. And the A is, for the time being, A is now some parameter. And so to make this model into the turbulent model, we add the dissipation. Nu is a viscous, and the kind of model viscous coefficient, which is constant. And F is forcing term, which is a large-scale constant. So we are going to deal with this equation as a hydrodynamic model for turbulence. So in this talk, I'm going to think of two kinds of the input of large-scale F. The first step, so F should be random, okay? Should be random forcing. So the first choice is F is a Wiener process, in which the Fourier coefficient of this forcing, F of kt, k is wave number, with a large scale, k plus minus 1, only set to Gaussian. Delta correlated in time and independent random variable with zero mean. under this setting, this equation can be regarded as stochastic PD, okay, which is very familiar model for the turbulence phenomena. So another choice of this equation is the forcing function is not the Wiener process, but they are regarded as a random variables defined on a certain probability space. The probability space is some sort of the sample space. So by this setting, we can see this equation as a random partial differential equations. So we are going to explain, in order to explain the schematically, the difference between these equations, I wrote some very simple figure. For SPD case, you can think of the solution in the high dimensional phase space. So when we choose the initial data and the random process, the solution is going like this. Okay? So by taking many samples and then going to the rough path, then after some time t, we can take ensemble average. This is how we obtain the ensemble average of SPD solutions. The another way, random PD case, the situation is somewhat different. In this case, we pick f and omega initial data and random forcing from some probability space, such as a Gaussian distribution or a uniform distribution. So, but if once we have determined the initial data and f from this function sample space, the solution is some sort of the mathematically solution. This is not rough. It is very smooth function is obtained. But so by taking this f1 omega 0 from some distribution, then we have the distribution of solution. This is the way how we see the solution as random PD. It looks very similar, but the meaning of ensemble average are somewhat different. So the next, okay, I still have time. Okay, it's just 30 minutes. Okay, good. So in the next 30 minutes, I'm going to introduce a numerical result for these SPDEs and a mathematical result for RPDE, and to compare these results. Okay, so here is a numerical simulation for the SPD case when A equals -2, where the entropy is implicit a conserved quantity. So this is a plot of omega. This is a plot of Hilbert transform omega, and this is the velocity field of B. And the viscous coefficient is very small, 2.5 to 10 to the -5th. Okay, when we look at this solution of omega, you can see a very sharp spike, like and the moving randomly from this domain. And sometimes it disappears and merges. This kind of a very randomly behavior can be observed in this solution. So the situation is much clearer when we see the Hilbert transform omega. In the middle of this kind of sharp edge, we can find a very sharp singular peak in this solution. Okay, so in terms of V, looks smooth because V is an integration of the vorticity, looks much smoother, but we can see still some sort of the randomly moving behavior. So when we check this solution, and the entropy for this randomly moving solution, L2 norm of the solution, which is entropy, is statistically stationary, which means the solution moves randomly, but on average, it stays on the same level. And also, we can see a sharp appearance and disappearance of moving sharp spikes. This may suggest us some existence of singular solutions in this equation. And so then, based on this numerical data, we are going to check if the scaling law of entropy cascade is observed. Okay, this is the next step. Okay, so the first step we need to think of is an energy cascade. So energy is very simply defined by this. This is a Fourier transform of U. And so then we take the K prime is some range of the spectra with some width delta K, wave number window delta K. So this is a plot of the long time average of the solution. As you can see, nu1 is the same. And nu1 is 2.5 to 10 to the -5th. So this is a decay of the energy spectra. So this picture shows that when the viscous coefficient is getting smaller, Okay, and okay, first thing we need to see is the existence of some cascading slope here, whose the decay rate is somewhat k to the minus third. K to the minus third is obtained from the dimensional analysis for the Euler or the one-dimensional equation, which agrees well the dimensional analysis with some correction. It's a very small correction here. And the next thing we need to check from this data is when nu1 is decreases as the solution approaches to the implicit case and situation, this inertial ranges expands. Okay, this is an indicator. It indicates the existence of energy cascade in this new turbulence, SPDE turbulence model. So when we compare this situation with the 2D entropy cascade of turbulence, which is a soap film experiment, you can see a clear k to the minus 3 slope in the inertial ranges. In this sense, our one-dimensional model of turbulence pulse is something similar to the 2D entropy cascade. Okay, so this is this model. This Omega commutation suggests us to the existence of entropy cascade in the limit of the viscous coefficient, limit of viscous coefficient. Okay, so when we look more closely about how the entropy is flowed along the wave numbers. So this is the definition of the entropy flux with respect to the Fourier spectra of omega and u. So this is a plot of this quantity. So this is a wave number. This is this value pi q. As you can see clearly, so when there appears a plateau region here, this means the constant entropy flux exists in this wave number, in the range of these wave numbers. And also, we could see this plateau region expands as the nu decreases to 0. This is also the same situation as the 2D entropy cascade turbulence. So here is a k to the minus third power law. And this is an entropy flux, which we can see a long plateau region that's suggesting entropy is cascade at a constant rate in the inertial ranges. In this sense, this model can provide a good numerical evidence of generating entropy cascade. So, but it is, unfortunately, it is much more difficult to compute the high-order statistics of the SPDEs because the solution is much more rough. And when we take the piece order moment of this solution, statistically, it is very unstable. And also, it is much more difficult to deal with this phenomena mathematically, such as recently I have shown the existence of invariant measure for this flow model, but it is still a mathematical abstraction. So anyway, so we have no information about the mathematical property of this energy cascading. So this is why we need to change the way how we introduce the random forcing as the random partial differential equations. Okay, the equation looks the same. It's the same. Okay, this is a one-dimensional model for Euler plus advection term, the random forcing. The difference is here. F and omega 0 initial data are chosen from some sample space, which has a certain probability measure. So the purpose of this talk, and the following talk is show mathematically rigorously existence of global solution for this equation. And then based on this mathematical argument, we can show that the existence of a stochastic process, omega of t, as a solution of the random partial differential equations. And also, so this is mathematically good result because this is a global existence. So based on this, we approximate this stochastic process with using some sort of the Galerkin approximation method with a generalized polynomial chaos. this is a very good numerical approximation to the probability space. Okay, so I'm going to explain this mathematical result and this numerical result and suggested by these numerical solutions. Okay, so we need also think of the more mathematical notations like function space in what follows. So when we write xmt, this is a set of the continuous functions from the time 0t to some Sobolev space. The norm is of this function space is given by the magnitude and the maximum of this u of t is given by this norm. Okay. And also, we introduce the same Sobolev norm, which is an mth differentiable function in L2 space, and the uxt is an average is always 0. This is the same as you have introduced in the Euler case. Okay, so this is when you read the mathematical notation showing next few slides, you have to think of this kind of notation can be defined by this. Anyway, so it is not so important it is very important for mathematicians, but it is not so important for physicists. Anyway, so and also this is a definition. Mathematicians always think of very carefully about the definitions of solutions. We introduce many kinds of definitions of solutions. The first one is a mild solution. This gives like an omega t satisfies this integral equation. This is a mild means this we didn't introduce. It doesn't include the time derivative of time of omega. But if it is integrable with time, then it is the same as the original constant, the original GCD-MG equations. So this is called a mild solution. Anyway, so this is much broader class of solution. Then we can make it a strong solution when the solution holds in this Sobolev space. And also when we consider the global, so when we say the model solution global, if the solution exists for all time. Okay, so this is the notion of the mild solution, a strong solution, and a global solution, which is a mathematical. It looks very difficult, but anyway, so you can say a mild solution is enough. Delta is a heat kernel. Yes. Okay, so yeah. Okay. Okay, so I'm going to show you some mathematical result. This is the main part of my talk, but you might not be interested in that, but I'm going to show the result. So the first step is an existence of unique mild solution. So A is a real number, and U is a positive real, and M is a chosen, and the Sobolev norm, the M's derivative solution. So if the if the initial data, forcing term initial data in this function class, then there exists some the time t such that the solution has a unique mild solution. This is a local mild solution because the t is limited depending on the initial data and the forcing term. So based on this mathematical theorem, we are going to think of some continuity of solutions with respect to the initial data omega 0 and the forcing term f. This is the reason why we consider this case is if we can make these two functions a random variable. So that means if we perturb these functions slightly, the solution needs to be continuous. So this is a wrong statement, but you can see here. If we consider two kinds of forcing term, F1, F2, and omega 01, omega 2 initial data, for each F1 and omega 01, we have a solution omega 1. On the other hand, when we had another forcing term F2 and another initial data omega 02, that gives us another solution omega 2. This theorem indicates that the difference of some norm of these two functions is bounded by the difference from the forcing term and initial data. This shows a continuity with respect to the forcing term and the initial data. This is a very important property to construct a stochastic process from the solution. Okay, so but we still need to make this solution to exist globally in time. So here is some, in order to do this, we have to show that the solution never blows up in finite time. So that's why we need some sort of a priori estimate to show the solution remains bounded. It looks very complicated, but it is important to see here that the solution, the Meyerl solution obtained here, is bounded by these terms, in which C is some parameter depending on the regularity and the viscous coefficient and time t, which appeared here. Then also, Pm is which is here. Pm and Qm denote the polynomials of the degree 3m having non-negative coefficients. Anyway, so this is the polynomials. Polynomial of this initial data and the forcing term. So this means once we have obtained the forcing term and initial data in this function space, the solution up to time t is bounded. This is a very important estimate to show the global existence. But let us note that at this point, A should be an arbitrary number, but in this case, we restrict our attention to the A equals to -2, where the entropy is, in this is the case, entropy is conserved. Okay, anyway, so this step, after this step, we can show the existence of unique solution. If A is -2, nu is positive, and M is some regularity, then when we choose F and omega 0 in a certain function space, then solution exists globally in time. Moreover, so the bound of this solution can be obtained here, which is similar to the a priori estimate. So up to this, mathematicians are very happy with this because solution exists globally in time. So next step we are going to investigate is to the existence of a stochastic process, because we now going to change this F and omega 0 taken from the probability space. So this is a mathematical result. If A equals -2 and nu equals greater than 0 for a given probability space, something like omega Fp, then the solution exists, and so the random variable taken here for any t, then there is a stochastic process omega from the sample space to the function space uniquely, such that the omega is L2 in this all time, and omega and eta and omega eta is a Meyerl solution to the constant Lax-Meyer equation. So this is a mathematical foundation to assure the existence of the stochastic process in the random PDE. So let us move to the numerical computation to approximate this stochastic process to observe its statistical properties. Oh, sorry. C is which C? C. Yeah. If C gets larger, if nu tends to 0, very large, but still finite. Okay. This is a subtle situation. But anyway, even if we introduce some nu, which is strictly positive, this is bounded. If nu is 0, that could be divergent. Yeah. Okay, so here we are going to idea how we approximate the stochastic process using Galerkin approximation. So here is some mathematical notations. So for generally, Z is a random variable from the sample space to the RD. F tilde is RD to the function space, which is a measurable function. So we can regard the random variable as a composition of this measurable function with F tilde. Then as a result of this, we can make the random variables as a function of RD to H prime Sobolev space. So then we are going to approximate this function using some Galerkin measure. Okay, so this is how we approximate one. So in the function Hm, the Sobolev space is approximated by the standard Fourier coefficients approximation, Fourier series approximation. On the other hand, in the probability space omega, we assume we approximate the solution with using a polynomial chaos expansion in L2PZ. This is an orthogonal polynomial. So the basis of this probability space is represented by the orthogonal polynomials. this depends on this also the choice of orthogonal polynomials depends on what kind of probability distribution we choose. For instance, when we choose the uniform distribution, this phi on m is a Legendre polynomial. So in this numerical simulation, we approximate the solution in the function space by using a Fourier series, and also we approximate the probability space by using a Legendre expansion. So in this sense, the approximation of omega in the probability space and t and time and x is given by infinite sum of Fourier spectra in the function space direction and the orthogonal polynomial direction in terms of the probability space. So this is a coefficient. Then we can, the coefficient which is an n and m is this kind of wave numbers. Then we have this quantity that gives us the function of t. So we are tracking the evolution of this coefficient by using a standard fourth order Runge-Kutta method. Okay, so the advantage of this computation is everything can be every statistical properties can be computed only one numerical simulation. For instance, when we use the GPC expansion for the solution I have explained in the previous slide, then the average is simply represented by this. We can just take the zeroth order of the coefficient. And also, we can compute the average of the Einstein spectra like this. We don't need to take ensemble average or long-time average. We just compute the Galerkin coefficient, omega hat, to obtain any kinds of statistical properties. In the similar, we can compute the average of the piece moment. Looks very complicated definition, but in basically, you may see the second moment, the fourth moment can be computed the combination of these Fourier coefficients. Okay, so everything, once we have computed the GPC expansion of the solution to this equation, by using this Fourier coefficient, the Galerkin coefficient, we can compute any kinds of ensemble average. This is the advantage of using a GPC approximation. Okay, so let's move to, we still have, how many? Oh. Okay, a few minutes. Okay, I'm going to skip faster. Okay, so here is the numerical result. So this is an ensemble average of the vorticity. So as time t, 2.5 at 0.5 and 0.5, then you can see a convergence to a very sharp solution as t goes to infinity. So we choose the random forcing from the uniform distribution. So when we look closer around this edge, this doesn't blow up. This looks very smooth. So because the nu is still large. Okay, the solution tends to be a stationary state with two peaks like here and there, and it is an invariant distribution of the stochastic process. Okay, so this indicates us the stochastic process is converging to a steady state distribution. That's why we are focused on the statistical property of this the steady state distribution for the solution. So here is a plot of the ensemble average. When we change the nu, as nu tends to 0, the sharp peaks are more singular, getting more singular. Okay, this is very similar to the peak pulse we see in the random and stochastic PD solution. Okay, so when we take energy Einstein spectra, we can see this is U and this is omega. So when we see the Einstein spectra, this is the k to the minus 3 and k to the minus 4. Then you can see inertial ranges appears when k nu tends to decreases. I'm sorry, this is no, this is omega. Sorry, this is omega. So this is omega. So when k to the third, fourth, and third, then there exists the inertial ranges appears. This is a good agreement of the scaling laws of the entropy spectra for SPDEs. Sorry, this is okay. It's correct. Okay, this is entropy. This is a velocity spectra. This is vorticity. Okay, this is great. Okay, this is an agreement with the scaling property obtained in the spectra for SPDs. Up to this slides, we can say the SPDE and RPD has provided us the similar cascading phenomena. Okay, so, but in this RPD, we can go further because we can compute the structure function by using a very smooth GPC approximation. So this is an SPD solution, which looks very random. But by using this structure, by using the solution to the random process, we can compute the piece order structure function by using some formula like here. This is the definition. I'm going to skip this definition. Looks very complicated. But anyway, so the point is we can do the same dimension analysis for this structure function. Then the SP of vorticity is RP. P is given by here. This is the dimension analysis. So we are going to compare the result of the structure function for the RPD solution with dimension analysis result. So this is the final slide for the comparison with the structure functions. So this is the structure, second order structure function, S2 and S2 omega and S2U. So when we see this is when we change the nu tends to 10 to the minus second and 10 to the minus fifth. You can see a very clear emergence of the plateau region, which is similar to R to the minus, this is 0.54. This is estimated from the numerical data. This R to the 1/3 is a dimension analysis data. It's somewhat different. This is 0.33, this is 0.54. That means there is some intermittency appears. So on the other hand, when we consider the fourth order moment, according to the dimension analysis, this should be R to the minus 1/3, but numerically this is almost plateau. So this is also showing the discrepancy with intermittency situation occurs in the vorticity. Okay, so that means this equation provides a very strong intermittency in the solution. Okay, so by using this intermittent exponent, we can say something about the singular limit. So this is a theorem by Uriel Frisch, which can be found in this famous book, The Legacy of A.N. Kolmogorov. In this book, he stated that the structure function of even order of the flow velocity v satisfies this critical exponents, and the inertial ranges extends with nu tends to 0. And also, the third one is very important. If for a certain p, the two consecutive exponents of this statistical loss is decreasing, then the maximum velocity diverges as nu tends to 0. This is a somewhat a mathematical argument relating to the exponent of the intermittency and the divergence of the singular limit. So when we apply this argument to our problem, we find a very interesting result. So according to numerical computation by using the GPC expansion, the exponent gamma 2, zeta 2 and zeta 4 is, zeta 2 is 0.54, zeta 4 is 0.05. That satisfies this condition. And also, we can also observe the inertial range is expanded. So that means, that implies that the vorticity function in the zero limit becomes diverged at some point. This is very consistent with the singular distribution of the average of solution. This suggests us that this singular limit is indicating the existence of singular solution when nu tends to 0. Okay, so this is a mathematical. This strengthens the mathematical argument about the existence of solution to the Euler equation, because this numerical computation, this model suggests us the existence of singular solution in the zero viscous limit. Okay, so this is my summary of my talk. We have proposed a one-dimensional model and some computed static properties. Thank you very much.